Hi. Today we're going to take a look at the second half of the matter and measurement unit. We're going to start talking about measurement with unit conversions. But first, as a quick do now to really close the book on separations, I want you to read both of these. Please pause if you need to. I'm going to start rather quickly, and then I'll go through these, see how well you can answer these two questions. I'm going to start with the one on the bottom left. Remaining on the filter paper, since I see a bunch of AQs, this indicates to me that water is present even if the words aren't actually there. But this S here, this means not dissolves. I mean, it means solid. But because we know that water is present, if something is labeled as a solid when other things are labeled as an aqueous, we can surmise that the solid does not dissolve in water, which means when you filter it, the particles are way too large to get through the filter paper, meaning this substance will be left behind. In the second question, you might want to consider, since we see this solid, using filtration again. The issue, though, is that if you read the prompt, it says that the solid is completely dissolved, a salt, in water. And there's no indication that it undissolved, meaning if we tried to filter it, the dissolved salt would go through the filter as well. So if we want to recover salt from a saltwater solution, we have evaporation and boiling as the suggested methods. And then if you go look at any answer keys, most answer keys are willing to accept distillation, although I still don't advise it and I don't like it as an answer. So I will put a sad face next to it because that's not really what distillation's for. Distillation is to separate two liquids. So to get our way into the new unit, unfortunately we have to start talking about a few numbers. These two measurements are ones that I went and researched online. This first one here is the radius of a hydrogen atom, which is rather small. And this is the average radius of Earth's orbit, distance from Earth to the Sun, basically. And I grabbed these two radii because, one, it's nice to use two radii, two of the same thing, but you can see very clearly that both of these numbers don't make sense. I can't really picture what 93 million looks like. I can't really picture what 0.00000002 looks like. Those numbers are incongruous with how our brains work. So even though an inch and a mile, I know what an inch and I know what a mile look like, the number kind of needs to agree with our brains in order for the measurement to make sense. And if you find yourself with a number that doesn't make sense, you may want to take advantage of converting it to a number that does make sense. If I were to turn the top one into a different unit, maybe I'd say it's 90 picometers or 90 angstroms or something like that. And then we have the astronomical unit for the one on the bottom, but we'll talk about that in a minute. And then I also did want to take a moment to talk about these two units. This is the standard system, which you may be familiar with, 12 inches to a foot, 3 feet to a yard, 1,760 yards to a mile, and then 16 ounces to a pound for good measure. None of these units have a lot of basis in, well, they all have a basis, but they don't really like roll off the tongue. They don't make sense. 1760, it's an odd number, well, it's an even number. It's a strange number to remember. The metric unit is kind of nice because it works on base 10. They don't use 10, they use 1,000, but of course 1,000 is just 10 to the third power. So I'll put a 3 there in parentheses as a suggestion. The idea being, if you're counting millimeters, a millimeter is a very small distance. It's like, what is it, the thickness of a fingernail or something. Once you get to 1,000, that number's kind of big, so we convert it into a meter, and then when you have 1,000 meters, again, that number's kind of big. We want to change it. And that's 1 kilometer. And then in the same way, if you have like a small number of kilometers, and then we would convert that into a meter. And the whole idea here is ending up with a number that makes sense. We like numbers that are somewhere between 1 and 1,000 if we can deal with it, or maybe 1,000th and 1,000. Why don't we switch? Well, it's actually a neat story. We tried to back, I think, in the 70s or 80s, and the cost to switching over every sign on every road, every speed limit sign, every sign everywhere, it just got a little expensive. And it wasn't really our hubris or our stubbornness or anything. It was really just a cost issue. If we took it in small chunks, I'm sure we'd get there eventually, which is why we're going to use the metric system in our class. Okay, it's not the only reason, but still. I did also want to talk about the reference tables. Welcome to the reference tables. If you have taken Earth Science, you are familiar with the reference tables. The first thing you need to know is it is always available online, and I'm going to try and make sure you have a copy in class whenever you can. You can use it all the time for everything. Never need to ask. Every test, every homework, every project, please just assume you can use it. You'll get a fresh new one on the day of the Regents, and it contains useful information about elements, compounds, and measurements as a whole. I'm going to do, in these videos, I'm going to make sure to put a link at the top right above my head every time the reference table is used. I'm going to try and do that. That link is a QR code to the reference table PDF. So if you ever don't have it, you just use your phone to go look at it and pull it up while you're watching to make sure that you know what I am talking about. And I suggest you pull it up now. Oh, look, the link is still there. So about measurements, every measurement needs to contain two parts. The first part's the magnitude, and that's the number portion, and then there's the unit, and that's the letter portion. Common units you're going to see here on Table D that we're going to use in this course, the symbol, the name, and what it measures. And then there will be modifiers to those units with numbers and prefixes found on Table C. That's what we're focusing on today. All right. We've talked about units, we've talked about magnitudes, we've talked about the fact that sometimes numbers don't make sense, so let's get into this dimensional analysis. Now, dimensional analysis is just, a bit of the tip of the iceberg with respect to the math of the course, but I'll try and take it in small chunks. The point is to change the value of the magnitude so that it makes sense to your brain. But if the number changes, the unit has to change too, right? You can't say, like, I'm going to convert 1,000 millimeters to meters and then also get 1,000 meters. That's not equal. Don't do that. That makes me sad. So usually what needs to happen is that if the number and the unit change, the number gets into a place you can imagine, and then we all have to be on the same page with what these units mean. Of course, we all have to agree on what a millimeter, a meter, a kilometer, a kilogram, a liter. We agree on what all these things are, and it allows us to talk about, measurements. So the idea is if you have 1,000 millimeters, that would be equal to 1 meter. If the magnitude goes up, the unit size goes down, and then obviously vice versa. If the magnitude goes down, the size goes up. So that's to say a millimeter is smaller than a meter, so then 1,000 is greater than 1. Number went down, unit went up. And then the idea also is that any conversion, when you do it successfully, the actual quantity you're measuring doesn't change. That is to say, the distance represented by 1,000 millimeters is equal to the distance measured by 1 meter. If it's not the same amount, well, then you didn't do it right. So in general, here are the steps for dimensional analysis. I'll let you read through them. Do use Table C for now. There is a bit of a check for scientific notation necessity. I would say use a calculator. I will show you what I mean when we get to a couple practice problems, but there they are. Pause if you need to write them down. So in looking at that step 3 that mentioned the word conversion factor and how you do this dimensional analysis, a conversion factor is a fraction that's mathematically equal to 1 that changes both the magnitude and the unit. So I want to take a step back to look at what 3 said because I think it actually helps. Target units get copied to the denominator. Check that the quantities match. So, yes. So let me just write it out for a quick example of what this would look like if you were doing, say, the one that we already know the answer to. So I know 1,000 millimeters is a meter. But let's say I want to convert 1,000 millimeters. Oops, I need an eraser because I can't spell. There. So going back to our steps, step 1 would be to write our given value. Then I'm going to write a time sign and a line. So this conversion factor, which is going to be this thing I'm multiplying by, is some fraction that is mathematically equal to 1. The rules say the unit that I started with is the unit that goes in the denominator. The unit that I'm targeting is going to go in the numerator, and then I need to write numbers in here that make sense. The numbers that we know to make sense are 1 meter is 1,000 millimeters. I will talk about using table C in a second. But then the idea is, you know, that this is technically, you could write this as a fraction if you wanted to, over 1. And then we just multiply across and multiply across. And what you should end up doing is that these two units always cancel, which is why you write the given units in your denominator. I also know that the 1,000 would cancel with the 1,000. I end up with 1 meter. These are the only things that didn't get canceled. So in looking at this, I will go through this process a little more. I think I skipped over one thing that I really wanted to talk about. Yeah, use table C to fill in a value for the prefix. So the real big idea here is this has to be equal to 1, as I said, this conversion factor. But when you're filling them in, I don't really like writing it the way that I wrote it here. In fact, I actually want to erase it and write it slightly differently, because I think most of us understand that 1,000 millimeters is a meter. But when we get into things like nano and pico, and if we even have to switch between them, it gets really difficult to do that and always get the right answer unless we're really good about writing writing these conversion factors. So if we're writing millimeters down here and writing meters up here, basically what I want to do is I want the stuff that isn't the meters to be the stuff that's the same. So I have milli here. I'm going to write 1 because every time I have that prefix, I want to write a 1 with it. And then I want to go over to table C, and then I want to find milli, and I'm going to write that number up here. So in other words, 10 to the minus third equals 1 milli. That's where this whole thing ends up equaling 1. If you make sure that you write a 1 where there's a prefix, and then you don't write a 1 where there isn't a prefix, this always works. And I'm going to show this on the next slide. Now, I mean, obviously that math gets a little bit more difficult to carry out, but that's why I'm saying use a calculator and use your parentheses. So again, going through our process, 350 centiliters. We're going to convert it to liters. You don't always have to write that multiplication sign if you don't want to. The centiliters gets moved down. The liters go up top. I write a 1 with the centi. Centi is equal to 10 to the minus second. I write 10 to the minus second up top. I multiply across, and I believe that comes out to be 3.5 liters. Of course, if we go through and show all the algebra, the centiliters cancels, and then it's just 350 times 10 to the minus second, or 350 times 0.01, or 350 divided by 10 to the second, however you want to do it. I'm not going to tell you how to do math. In doing the second conversion, well, you know what? If you want to pause the video, I'm going to mention this now. It's a good time to see if you can do it, because I'm about to show you, but if you know how to do it, right, you can try it yourself and then check to make sure you did it correctly. Right. So 0.19 grams, we're going to convert to milligrams. We're going to put grams on the bottom. We're going to put milligrams up top. We're going to put a 1 there. Again, milli is equal to 10 to the minus third, or write 10 to the minus third on the bottom. Yes, dividing by a negative exponent. Really weird, really uncommon, but we can do that. Multiply by the 1 on the top, divide on the 1 on the bottom. Use your calculator to help you if you need. The grams cancel, and I believe we end up with 190 milligrams. Hope you got it right. So that's basically the process of converting. We're only going to really deal with the metric units you find on table C. If we ever get outside that, of course, you can ask for what the conversion will be or what the value of the prefix is. But the whole process is units exist and you have to use them from here on out. Every measurement needs to have both of those. If you're just using a number, that's one thing, but if you forget your units, that's not good. Don't do that. Use the reference tables as much as you can, as often as you can. Match your units with the denominator. Match your target with the numerator, because that's a big difference. And then make sure that that prefix value matches vertically, as in milli and 10 to the minus third, and kilo and 10 to the positive third. And that's the whole process. Thanks for watching.